Hello, my name is Kimberly Ying and I'm a PhD student at the University of Florida, advised by Dr. Christy Boyer. Today I will be presenting my Chi late-breaking work titled Understanding Students' Needs for Better Collaborative Coding Tools. Collaborative coding has proven beneficial in both industry and educational settings. We define collaborative coding as two or more people working on a program. This involves all aspects of the collaboration, including planning, sharing and organizing files, as well as editing source code. Many applications have been created to facilitate collaborative coding, but little research has been conducted to evaluate these applications, especially in the context of education and novice users. We speculate that many of these applications are designed with industry needs in mind and are tailored toward power users. In this preliminary work, we ask, are students' needs being met by existing applications for collaborative coding? Collaborative coding can happen in many different contexts. The collaboration could be synchronous, with programmers working together simultaneously, or asynchronous. Synchronous collaboration can happen in person or remotely, with remote collaboration commonly facilitated by screen sharing applications or real-time editing software, through which two or more programmers can work on the same source code and see the edits updated live. Asynchronous collaboration is generally supported by source or version control in combination with online repositories, allowing development teams to access and edit the source code while tracking changes. And this context could change throughout the same project. For instance, collaborators might decide to work synchronously on a particularly challenging part of the project and asynchronously for most other tasks. Our research questions were, what applications are students using to facilitate their collaborative coding endeavors? And what are the strengths and weaknesses of existing collaborative coding applications? Many evaluations of existing collaborative coding software focus on descriptions and feature sets and commonly leave out user testing. On the other hand, some collaborative coding tools specifically designed for students have had positive user evaluations, but these tools are not widely used. Therefore, we must understand how students are using commercial software and whether their needs are being met. This preliminary study differs from those mentioned because it crowdsources the applications to be evaluated instead of selecting applications based on the author's own experience or web search. Students and faculty completed an online survey and were asked what applications they or their students use to collaborate on programming projects. This approach is beneficial in two ways. One, it provides a more realistic view of what applications are being used by students. And two, it allows for a more holistic understanding of the collaboration process, since respondents included applications they use for organization and communication in addition to source code editing. Students were asked whether they ever collaborated on a programming project. If they answered yes, they were asked additional questions, including free response questions about the applications they've used and the application's strengths and weaknesses. All respondents were also asked about what they felt were the most important features for collaborative coding applications. The faculty survey questions were synonymous with the student survey questions. The differences are here in green. Participants were recruited in two ways. First, we compiled a list of 100 computer science programs in the United States and searched online for one contact email per institution. Then the recruitment email was sent to each contact in the hopes that they would forward the email to CS students and faculty. Second, the recruitment email was sent to the 60 members listserv, an opt-in mailing list managed by the Association for Computing Machinery, Special Interest Group for Computer Science Education. The 60 community includes members from both US-based institutions and international institutions. These are all the participating institutions. 31 unique institutions responded. 16 were from the list of 100 institutions that were directly contacted, and the remaining 15 we assume are from the listserv. We had 149 total responses, 126 of which were students and 23 were faculty. Over 50 collaboration applications were mentioned by survey respondents. This table shows the range of application types mentioned with specific examples. Application types included everything from source code editors to chat messaging clients. The most popularly reported tools were those for version control, with 68% of students mentioning Git and/or GitHub specifically. GitHub is helpful for project management, allowing for organization and accountability through issue tracking and peer review. While many students said Git or GitHub was easy to use, about 20% explicitly stated that it was difficult to learn. Students also expressed concern about themselves or their collaborators inadvertently ruining the whole project. Another common weakness reported for versioning tools was merging issues. Student anxieties about using versioning tools may have led some students to use more user-friendly or familiar applications that were not necessarily designed for code collaboration, such as Google Drive and Google Docs. Over 10% of the students mentioned using Google Drive or Google Docs specifically. Students said they were easy to learn and use, quick to set up, and work everywhere. However, as they were not designed for code collaboration, they do not have syntax or programming language support and do not allow editing certain file types in the browser. Students also mentioned it's hard to manage versions and is not integrated with GitHub. 2 students did not mention currently using these applications for collaborative coding, but used them to describe their ideal development tools, writing, "I wish there was a Google Drive but for development," and "something like a Google document would be much better since both parties can edit code at the same time." Some students and faculty mentioned their collaborations were mostly done through pair programming. Traditionally, this does not require the use of any additional tools beyond what a single programmer uses, but some students revealed a desire for additional support. One student wrote, "Collaborating in person is great, but it would be nice to both be able to use a keyboard." 2 other students also liked pair programming, saying it was familiar and reliable and that it was good because they were both looking at the same thing, but that it was difficult for the non-driver to point things out. Even in cases of in-person collaboration, there's potential for technologies to create a more efficient workflow. From this preliminary analysis, we conclude that many students' needs are not being met by current tools, and therefore more novice-friendly collaborative tools are needed. Students reported challenges with co-located and remote synchronous collaboration, as well as with versioning tools for asynchronous collaboration. Although applications have been created for an educational collaborative context, these tools are not widely used, and so we urge those creating commercial applications to be more deliberate in considering the novice user. To gain a deeper understanding of students' needs, future work will include conducting focus groups and user studies on common collaborative tools. Since steep learning curves and difficult setups were among the most pervasive application weaknesses, we plan to observe students with no prior experience using these tools. That concludes our talk. We'd like to acknowledge NSF for funding this research and thank the members of the Learn Dialogue group for all their help. Thank you for listening.